Alright, students, it's now time to review in-class exercise 1. Okay, so for the first question 1A, you are asked to write an expression for the KSP of PBCl2. I think this should be quite straightforward directly from the notes. Okay, so you know that one equivalent of PBCl2 will give you one equivalent of Pb2 plus and two equivalents of chlorides. So based on the KSP expression or based on the stoichiometric ratio, what you're going to get is KSP for PbCl2 will therefore be equals to the concentration of lead-2 plus raised to the power 1 multiplied by the concentration of chloride squared. Yeah, so in this case for the units, because you are multiplying a concentration term and another concentration term raised to the power of 2, so in that case the units will be mole to the power of 3 and then dm to the power minus 9. Okay, and very quickly let's look at 1b. You have 10 cubic centimeters of samples of saturated solution for each of PbCl2 and PbI2 evaporated to dryness, and then you're supposed to determine by calculation which solution produced the larger mass of solids. Okay, so based on this KSP expression alone for PbCl2 and PbI2, I think the first thing we can do is let the solubility of PbCl2 and PbI2 be X and Y respectively. I think if we work out this way, it's clearer so that we're not confused by the two. Okay, so in this case we are going to get 4x cubed equals to 1.7 times 10 to the power of minus 5, 10 to the power of minus 5. Okay, and then for PbI2 we're gonna get 4y cubed equals to 9.8 times 10 to the power of minus 9. Okay, so from here we will calculate x. Okay, so we'll then calculate x to be x is therefore equals to the cube root of 1.7 times 10 to the power of minus 5 divided by 4. Okay, so in that case I'm going to get x to be 1.62 times 10 to the power of minus 2 moles per dm cube, and then using the same method, cube root 9.8 times 10 to the power of minus 9 divide by 4. I'm going to end up with 1.35 times 10 to the power of minus 3 moles per dm cube. Okay, so if we multiply this value by the relative formula mass, okay, so in terms of grams per dm cube, then we're going to be 1.62 times 10 to the power minus 2 multiplied by the mR of PbCl2. So if we look at it should be 207 point something plus 35.5 times 2. Okay, so you can work out yourself. You should be able to get 278.2. Okay, so that's the MR, and then for PbI2 it will be 461. Okay, you should be able to look it out yourself as well. Okay, so for lead chloride in 10 cubic centimeters, so in 10 cubic centimeters, mass of lead chloride, okay, will be equals to, so you scale it, so that's 1.62 times 10 to the power minus 2. You scale it by 100, okay, and then you multiply it by the relative formula mass, and that's 278.2. okay, and then you will get 0.0451 grams. Okay, you do the same way. So in 10 cubic centimeters, mass of PbI2 will be equals to 1.35 times 10 to the power minus 3, scale it to 10, and then multiply by the relative formula mass, 461, and then I should be able to get 0.00621 grams. Okay, or you can write it as 6.21 times 10 to the power minus 3. Yeah, so with this, you can conclude that lead chloride will give a larger mass. Okay, I think earlier on I forgot to mention, like very quickly I can discuss this with you. I forgot to mention how 4x cubed is being obtained. I mean, in case those of you who are not very sure. So I think first we can easily write out an equilibrium expression. So PbCl2 equilibrates to give us Pb2 plus aqueous plus 2Cl minus aqueous. Okay, so this is solid. So we assume that x moles dissolved. Then we're going to have x here and then 2x. Okay, and then we substitute this into the KSP expression. This will be x, and then this will be 2x whole thing squared. Okay, so we multiply this together. This will be 4x cubed. Okay, you don't have to memorize. All you need to do is just to work out on the spot. I think it's faster that way. Okay, so the next thing we're going to do is question 2. So first, again, standard questions, supposed to write a KSP expression for silver chloride. So KSP of silver chloride, it will be concentration of silver plus raised to the power of 1, concentration of chloride raised to the power of 1. The units will be moles squared dm minus 6. Okay, and then for B, you were told that an excess of silver chloride was stirred with 0.5 moles per dm cube of silver nitrate until equilibrium was established. Calculate the chloride concentration in the resulting solution, given that the KSP is 2.0 times 10 to the power minus 10. Okay, so we work out the same way. We write out an equilibrium expression. Okay, silver chloride equilibrates to give us silver plus aqueous and chlorides. Okay, so we assume that A moles dissolve, so we're going to have A here and A here. Okay, but in the presence of 0.5 moles per dm cube of silver nitrate, in that case we need to bump up the amount of silver plus. We need to add 0.50 here because originally the solution already contained 0.5 moles per dm cube of silver nitrate. So in that case, you would expect less silver chloride to dissolve because the presence of silver plus will suppress the dissolution of silver chloride. Yeah, so given that, what you will do is you will write out, or you substitute this into the KSP expression. So you're going to end up with A plus 0.50 multiplied by A is equals to 2.10 times 10 to the power of minus 10. Okay, and because A is a much smaller number as compared to 0.50, so what you can do here is you can approximate the whole expression to be 0.50. A equals to 2.10 times 10 to the power of minus 10. Sorry, it's actually 2.0, not 2.10. Okay, so we're going to correct this, 2.0, 2.0. Okay, and then of course here A will be equals to 4.0 times 10 to the power of minus 10 moles per dm cube. Okay, so this will be the concentration of chloride at equilibrium when equilibrium is established when silver chloride is added to 0.5 moles per dm cube of silver nitrate. Okay, so I think that should be fine. And then after that, you have a part C, which asks you to describe and explain how the solubility of AgCl is affected by ammonia and by adding sodium chloride. Okay, so I think adding sodium chloride wouldn't be a major issue because when you add sodium chloride, you are actually introducing not only sodium plus, but you're introducing chloride. And chloride is actually a common ion. in silver chloride dissolution. So in that case, the addition of sodium chloride will suppresses the dissolution of silver chloride, making silver chloride less soluble. So it works the same way as a solution which already contains silver nitrate, and you are trying to dissolve silver chloride. Okay, and what happens when you add aqueous ammonia? If you flip over your data booklet to the second last page under QA, you will notice that the role of aqueous ammonia is to allow you to test for the solubility or for the identity of silver halide. So silver chloride can dissolve in excess ammonia. Silver bromide partially soluble. If you add concentrated ammonia, then silver bromide will dissolve. But for silver iodide, it's insoluble in both aqueous ammonia and concentrated ammonia. Yeah. So why is that the case? Yeah. I think the story is quite similar because of complex formation. Okay. So if you look at this particular expression, let's call this equilibrium 1. So we're going to have another equilibrium operating, which I will call it equilibrium 2, when silver plus aqueous will react with two ammonia molecule in the molecular form. They will form a complex. This complex is known as diamine silver plus complex. So I'm going to have a silver here and then two ammonia ligands. Okay, so when we mean two ammonia ligand, we are actually saying that the ammonia will form a dative covalent bond with the silver center. Okay, so you will learn a little bit more about this in transition metal chemistry. Yeah, so when you add ammonia, equilibrium 2 will operate. So it will lead to the formation of diamine silver plus complex. So this is similar to removing silver plus from equilibrium 1. Yeah. So according to Le Chatelier's principle, the removal of silver plus in equilibrium 1 will cause the position of equilibrium of 1 to shift to the right, enhancing the solubility of silver chloride. So in that case, adding excess ammonia will result in the formation of this particular complex, and therefore increases the solubility of silver chloride. Okay, so I hope this is clear for you. You roughly have a sense of what exactly is going on when we are dealing with KSP. Okay, then finally we are looking at question 3. So for question 3, you were told that an alkaline solution is saturated with magnesium hydroxide and magnesium phosphate. So you probably want to take note of these two salts. Of course, magnesium hydroxide is not really a salt, but it's a hydroxide. So given that the pH of this solution is 12.0 at 25 degrees Celsius, yeah, so the focus here is 25 degrees Celsius. Why is this important? Because if you remember from the last page of your notes, you were told a special relationship which you will learn in JC2, that is pH plus POH is equals to 14.0 at 25 degrees C. Yeah, so and remember that pH is actually minus log base 10 of the concentration of H plus. Then of course POH is minus log base 10 concentration of OH minus. So in this case, we can actually obtain POH to be 2.0. Why is this important? It is important because we can straight away determine the concentration of OH minus to be 10 to the power of minus 2.0. Then you'll be asking why is this important again? Okay, so this is important because from here we can determine the amount of Mg2 plus which is being contributed from magnesium hydroxide. Okay, so if you are able to calculate the concentration of Mg2 plus contributed from magnesium hydroxide, I think that will make our problem a lot easier. Okay, so in that case, we're going to have Mg2 plus multiplied by hydroxide squared, and this is actually equals to the KSP, which is 1.80 times 10 to the power of minus 11, and we can easily determine the concentration of Mg2 plus to be 1.80 times 10 to the power of minus 11 divided by 10 to the power of minus 2.0 squared, and you can easily get 1.80 times 10 to the power of minus 7 moles per dm cube. Okay, and you might want to be aware that for a system at equilibrium containing two different salts, the amount of the salts of one ion must be consistent for both equilibrium. Okay, so what we are trying to say here is that okay, because we have a salt contain, okay, we have a system that contains magnesium hydroxide. So so we have magnesium hydroxide here, which is a solid, equilibrate to give us Mg2 plus aqueous plus 2OH minus aqueous. Okay, then we also have magnesium phosphates over here, two solids, and then equilibrate to give us 3Mg2 plus aqueous plus 2PO4 3 minus aqueous. Okay, so for a system at equilibrium containing two salts, in this case magnesium hydroxide and magnesium phosphate, the amount of Mg2 plus at equilibrium must be able to satisfy both. So it cannot be the case where one equilibrium have one concentration of Mg2 plus, the other equilibrium have another concentration. Yeah, so this is totally nonsensical. Yeah, so in this case, the 1.80 times 10 to the power of minus 5 must satisfy both equilibrium. Okay, so so this will satisfy the first equilibrium as well as the second equilibrium. So I hope that is clear to you. Okay, then with that, you know that the value of this must be the same as the value for the other equilibrium. So we can use this to equate it to the KSP of magnesium phosphate. Yeah, so with that, we're going to write out the KSP for magnesium phosphate. So that will be Mg2 plus cube and PO4 3 minus squared, and this will be equals to 1.01 times 10 to the power minus 25. Okay, and for the concentration of magnesium 2 plus, it has already been determined earlier on. It's determined to be 1.80 times 10 to the power minus 7. So the whole thing cubed, and then of course PO4 3 minus squared. Okay, and this is equals to 1.01 times 10 to the power minus 25. Okay, so if you punch your calculator, you will be able to calculate the concentration of phosphate to be 0.004161 moles per dm cube. Okay, and because one equivalent of magnesium phosphate gives you 3 equivalents of Mg2 plus and 2 equivalent of phosphates. Yeah, so in that case, therefore the solubility of magnesium phosphates will therefore be whatever value we have calculated divide by 2. Okay, so it will be this phosphate, magnesium phosphate 0.004161 divided by 2, and you'll give us 0.00208 moles per dm cube. Okay, so I hope you guys are clearer about how to go about solving questions related to KSP, and then do look forward to the next video on in-class exercise 2.